Hello, today we're going to continue with our series on quantum mechanics concepts. This time we're going to be looking at the energy operator, which is called the Hamiltonian, and we're also going to be seeing how states vary with time. We go back to our tried and tested formula that the Hermitian acting on an eigenvector, which we're now starting to call a wave function, will give us an eigenvalue multiplied by the same eigenvector. This is Hermitian, this is an eigenvector, this is the eigenvalue, and in physics terms this means that there is an operator, either a measurable or nature itself, acting on some kind of state which is a superposition of basis vectors, and it produces one of those, and you know which one it produces by the value of lambda, the eigenvalue that it gives up. So in this particular video we're going to be interested in an operator which acts on a state to tell us what the energy is. So now the eigenvalue is going to be energy. I just want to remind you of a formula which we developed when I developed the Schrodinger equation. There are two types, the time-independent and the time-dependent Schrodinger equation. I'm looking at the time-independent. This means it won't have a time term in it. And this says that minus h bar squared, where h bar is the reduced form of Planck's constant, divided by 2m, where m is the mass, times d2 psi by dx squared, where psi, of course, is the wave function. I could put it in Dirac notation, but I won't at the moment because we didn't derive it like that, plus a potential acting on psi of x is equal to the energy acting on psi of x. That was the time-independent Schrodinger equation, which was derived in one of the first videos I did. I actually derived it from classical mechanics, and I said that was actually the wrong thing to do, because you should strictly derive classical mechanics from quantum mechanics. But I showed at least how this was consistent with our understanding of classical mechanics. Now I could rewrite this, of course, like this: minus h bar squared over 2m, d2 by dx squared, plus u of x, all acting on psi of x, is equal to E psi of x. And if I put those psi's now in Dirac notation, you can see we've got a format which is equivalent to this format here. So we've got our eigenvectors psi, we've got our eigenvalue E, and this now is our operator H, and that is known as the Hamiltonian. Now we could have got to that Hamiltonian by recognizing that that is the operator that gives us energy. And what is energy? Energy is kinetic energy, which is p squared over 2m. That's the same thing as half mv squared. It works out the same way. It's p squared over 2m, where p is the momentum, plus the kinetic energy, which I will simply call v. And as always, we will simply be working in one dimension, the x direction, to keep things simple. Well, we worked out in the last video what P is. P is minus IH bar d by dx. So we can now say that this is minus IH bar d by dx all squared, which is effectively what P is as an operator. We're going to make these operators now, times 1 over 2m, which is this term here, plus v. And that means that h is going to be equal to, well, minus I squared is minus 1, so that gives you a minus. H bar squared is h bar squared, and then this term here becomes d2 by dx squared, and of course this is all over 2m. There, plus u, or v, as the case may be. So that again is our Hamiltonian, which we derived or showed to be the case from the Schrodinger equation just a few moments ago. So this is the Hamiltonian. It's the operator which is going to drive out one of the energy states. So let's consider a state which is an eigenvector or wave function, and it may vary with time. Now it may not, of course, in which case it will just stay in that state forever. But let's suppose it does vary with time. So as time goes by, this state changes. Now, how is it going to change? So far we have regarded operators as things that we do to a system in order to measure. So we apply an operator, and that is a measurable, and that chucks out an eigenvalue. But of course nature itself does things to states, and in doing so it is essentially represented by the action of an operator. So what we could say is that nature acts on state A to produce after time t another state which is the operator M1 acting on A. Similarly, if we have a state B and that varies with time, then over time t, that is going to become M1B. Or you could say, let's take the bra vector of B, over time that will become the bra vector of B, and then you have to take essentially the complex conjugate, which for an operator means taking the, you dagger it, it is the transposed complex conjugate of the operator. Now I want to look at the inner product of B with A. And over time, of course, both B and A are going to vary. So over time we are going to get the bra vector of B will become bra B M operator dagger, inner producted with the time evolution of A, which is M A. I did call these M1s and I've dropped the 1 because it's always the same matrix, so it's the same thing. Now, here is a postulate of quantum mechanics. Even though A and B may change with time, the relationship between them does not. If B is orthogonal with A, it will always be orthogonal with A after any amount of time. So the actual states change, but the relationship between the states does not change. So the inner product of B with A remains the same over time. That is a postulate, which means that this actually must equal this because it doesn't change. The inner product doesn't change. And the only way for that to happen is if that is the identity matrix. Because remember, we showed in the previous video that the identity matrix acting on a vector A simply gives you back the vector A. So that means that M dagger M equals the identity operator I. But in the very first video of this series, I think it was, I introduced you to a special type of matrix where I said that U dagger U equals I. And I said any matrix where you take its Hermitian conjugate, that is, you do the transpose and the complex conjugate, and you multiply it by itself, if it gives the identity matrix, then it has a special name. It is called the unitary operator. So now we know that the operator that is impacting on A over time and changing its state is a unitary operator. So if we start with a state at time t equals 0, so we'll call that psi 0 for time t equals 0, and we let it evolve over time t, then it will become a state which we will call ut psi 0. In other words, ut is the unitary operator which acts on the original state to produce a new state, which is ut times t0. Ut because it's the unitary operator acting over time t. But let's just think about this. By the same argument, if we take our state and we operate it over time t which equals 0, that is to say we don't let any time pass at all, then we are going to get that will evolve into u0 psi 0, where u0 is what happens if you don't let any time go past at all. Well, if you don't let any time go past at all, then psi 0 doesn't change. Consequently, u0 must equal the identity operator, because the identity operator acting on psi 0 just gives you psi 0. So we know that the unitary matrix, when no time has gone past at all, is simply the identity operator. So now I want to ask the question, what happens if we take our state at psi 0 and let it evolve over a time which I'm going to call epsilon, where epsilon is a very, very, very short amount of time. It is less than a blink of an eyelid. It is the most minuscule fraction of time. Using the same convention, that means that the change will be u epsilon psi 0, so there will be a small change to psi 0, because there has been hardly any change in time. And what is u epsilon? Well, if it had been time equals 0, then u0 would have been I. So I'm going to say that it's basically I, which it would have been if there'd been no time change at all. But because there's a teensy-weensy amount of change, I'm going to say that you need to add to that a minus I epsilon h bar. I'm not telling you what h is yet. And by convention, we put a Planck's constant, or reduced Planck's constant, underneath. So essentially, I've got an operator here, which is the identity operator, and this is an operator, so this term here must have an operator in it as well, which we'll call h. Epsilon represents the fact that it's a very, very small change, and the kind of minus I over h bar are essentially there for a combination of consistency and also to make sure that the operator is indeed Hermitian. So I've left the formula for u on the board because I now want to ask what u dagger u is. Well, we know it's the identity operator I. So that means that I is equal to u dagger u. Well, what's u dagger here? That's going to be I, because the Hermitian conjugate of I is I, there is no change, plus I epsilon h dagger, because you need to dagger this, it being an operator, these are all operators, divided by h bar. So that is essentially u dagger, this term here. And that we've got to multiply by u, which is simply just this term straight. I minus I epsilon h hat. But no dagger, of course, because it no longer has to be complex conjugated. So now let's multiply that out. That means that we've got that I on this side is equal to I times I, which is I squared. But I squared is simply I. I is, don't forget, the matrix equivalent of 1. If you multiply it by itself, you just get the same number back. Same with I. I times I is I. Then we've got a combination of terms here which will give us plus I epsilon over h bar of h dagger minus h. That's this term and this term. And then we're going to get plus times minus, we're going to get a minus this term times this term. But without worrying about multiplying it out, what we're going to get is a lot of numbers multiplied by epsilon squared. Epsilon times epsilon will give us an epsilon squared term. Epsilon is a very, very, very tiny number by definition. Epsilon squared is so tiny, it makes no difference at all. We can ignore it. Any higher order terms of epsilon can be pretty much ignored. So let's have a look at this equation. We've got that I equals I, which means that that term must equal 0, because we've already got I equals I, so that can't have any impact at all. Well, I epsilon over h bar doesn't equal 0, so h dagger minus h equals 0, which means, of course, that h dagger equals h. If h dagger minus h is 0, h dagger equals h. And what is that? That is the condition for a Hermitian matrix, which means that h is an observable. And of course, it turns out that it will be the Hamiltonian. So now let's think of a state, psi, which is at time t plus epsilon. We're not going to start at time t0 now, we're just going to start at any old time t, but we're just going to let another very, very tiny time interval pass. So this is time t plus epsilon, and we know that that is going to be equal to the action of the unitary operator epsilon on psi at t. So you take psi at t, you act on it by u epsilon, and you get a new state which is at psi t plus epsilon. That's a little bit later in time. Well, that means that psi t plus epsilon is going to be equal to u, which we know is the identity operator, minus I over h bar epsilon h acting on psi of t. So let's write that out. That means we've got psi of t plus epsilon here is equal to I acting on psi. Well, I acting on psi is simply psi. There's no change. When the identity operator acts on psi, you get no change. And then here we've just got minus I epsilon over h bar h of psi acting on psi of t. Now I want to take this term and bring it on this side of the equation. So I've now got psi t plus epsilon minus this term here. You bring it on the other side, you change the sign, is equal to minus I epsilon over h bar, the Hamiltonian h acting on psi of t. Now I'm going to divide both sides by epsilon. So this side gets divided by epsilon, and when I divide this side by epsilon, of course, the epsilon just disappears. Now then, what have we got here? We've got psi at t plus epsilon minus psi at t, and epsilon is a very small time difference. So we've got the change in psi is the top line, and epsilon is the change in time. What is that in our ordinary language? That's just the rate of change of psi with t. It's d psi by dt. This is the small change in psi. This is the small change in time. And that is equal to, and I can put that in like that, that is equal to minus I over h bar h psi t. And that is the time-dependent Schrodinger equation. And I can, of course, I can multiply by h over minus I on both sides, so as to get rid of this term here. And then, of course, if I multiply top and bottom by I get I at the top and minus I squared, which is just 1 at the bottom. So now I've got that IH, that should be IH bar d psi by dt is h psi. So once again, we've now derived that the Hamiltonian operator is IH bar d psi by dt. And just for comparison purposes, can I remind you that minus IH bar d psi by dx equaled the momentum operator acting on psi. So minus IH bar d by dx is the operator p, plus IH bar d by dt is the Hamiltonian. So the Hamiltonian here is actually responsible for the way things change with time. I now want to pause to deal with another concept in quantum mechanics called the expectation value. Now, the expectation value sounds as though it might mean the expected value, but that is what it certainly is not. A better term would be average value. If you've got any kind of thing like a toss of a coin or the throw of a dice, the average value, if you throw the dice several times, if you toss the coin several times, the average value that you will get will be given by the sum of lambda I, which is the numbers you can get from the outcome, times the probability of getting those numbers in the first place. Let me just illustrate, first of all, if we take coins, heads and tails. If I assign +1 if you get a head, and minus 1 if you get a tail, then of course what are you going to find if you toss the coin 10 times? On average you'll find you get 5 plus 1s and 5 minus 1s, which means that the average value will be 0. And that of course is a number you can never ever get. When you toss a coin you never get 0. I suppose that's the equivalent to the coin falling on its side. You either get a plus 1 head or a minus 1 tail. But the average, or the expectation value, but certainly not the expected value, is 0. And if we use this up here, what we would say is that you do the sum of the number you can get times the probability you can get it. Well, one of the numbers you can get is plus 1, and the probability of getting it is a half. When you toss a coin, there's a 50% chance of heads or tails. So it's plus 1 times a half, and you add to that minus 1 times a half, and you get 0. What happens if you throw a dice many times? Well, of course, we know that there are 6 numbers you can get, and the probability of getting each number is 1/6. There's a 1 in 6 chance of getting any given number. So what we're saying here is that the average will be equal to the number 1 times 1/6 plus the number 2 times 1/6, these are multiplies, plus the number 3 times 1/6, and so on right the way to 6 times 1/6. And that of course is just 1 over 6 into 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is equal to 1 over 6. This comes to 21, and that's 3.5. So the average value of the numbers that you will see on the face of a dice, if you throw it many times, the average value is 3.5. If you add up all those numbers and divide by the number of throws, it will come to 3.5. But of course, you will never get 3.5 when you throw a dice. It's physically impossible to get the number 3.5. So it certainly isn't the expected value. It is the average. But we call it the expectation value. Now I just need to remind you that we have shown that the eigenvalue, or the wave function, can always be expressed as the sum of probability amplitudes multiplied by the basis vectors. And you have to use all. It's a complete set of basis vectors, because this is the superposition of all these states with a probability amplitude for each of the basis states. And we've also shown that alpha I times alpha I star, which is essentially this term squared, whenever you square something you multiply it by its complex conjugate, is essentially the probability of getting the state xi. It's the probability of getting that particular state. So now I want to consider the time-honoured equation. An operator acting on a state psi will give an eigenvalue multiplied by the state psi. But to be complete, what we ought to do is to just put little j's here, because what we mean is that there will be several eigenvectors for this operator. With spin there were just 2, but we've already encountered situations where there can be an infinite number of possible states. So the operator acting on a state is equal to an eigenvalue for that, which will be different depending on what the state is that we are looking at. So every state, every eigenvector will have its associated eigenvalue. And we want to know, if you act on this state enough times, what is the average eigenvalue that you will drive out of that process. So we essentially want to know what's called the expectation value of m, and that is written in that way with 2 angle brackets. That is the expectation value. It is essentially the average value of the eigenvalues that are generated whenever m acts on this eigenvector psi. So let me derive this beast, psi m psi. You may recall that we used this to show that this would produce a real number if m were Hermitian. We've done that before, but we're going to do something different with it this time. Well, remembering of course that psi is equal to the sum over I of alpha I xi. This means that the bra vector of psi here can be written as the sum over I. We need the bra vector of xi, and then this has to be complex conjugated, so it's alpha I star times m, and now we need psi, which is the sum over j of alpha j xj. We can always bring the numbers on the outside because these of course are just going to be numbers. They are going to be real numbers as it happens, but so we're going to have a sum over ij because we've got sums I and j. We've got alpha I star and alpha j. And then in here we've got xi m xj. xi m xj, because those two numbers have been brought outside. Well, we know that when m acts on xj, that will simply give us lambda j, because that's exactly what a Hermitian operator does on a basis vector. It will give us the lambda of that basis vector. And that number is just a number, so that can come outside here. And that just gives us the inner product of xi with xj. Well, we've done this many times before. When I does not equal j, this term becomes 0, the whole thing becomes 0. So this only matters when I equals j. So, and when I equals j, then the inner product of xi xj becomes 1. So essentially we can rub out this term here and simply put the lambda j here, and it's summed only now over j. It only matters when I equals j. But hang on a minute, we've got the sum of this term here, which is the probability of getting lambda j, times lambda j. And that is our definition of an average. This was the probability. This is our definition of average. So what we've effectively shown is that this term here is what derives the average value of m, or the expectation value of m. Now I want to explore how states vary with time. We'll begin with a form of the famous equation we've had before. This is going to be the Hamiltonian. The Hamiltonian is Hermitian. It acts on an eigenvector to produce an energy state of that eigenvector. And what we can do is to give each of these little subsets I, because there will be different states and each of them will give a eigenvector, a different eigenvector. And we just remind ourselves of the fact that we have described the state as always a sum over j of the probability amplitude j and the basic, or the basis state xj. You sum those and that is psi, because I'll say it again, psi is a linear superposition of all the states with a varying probability amplitude for each. So let me now find out what this is. This is, how does psi change with time? Well, that's going to be equal to, on this side, sigma j. Now, which of these two is going to change with time? Well, the basis states won't. Those are just basic states. This is the probability amplitude. It's the probability amplitude that changes with time. So you will get that the change of psi with time is equal to the sum of the change of probability amplitudes with time times the basis vector, which doesn't change. And that formula you'll need to remember because we're going to need it a bit later on. So I've written it out again at the top of the board. Now let's just remind ourselves of the time-dependent Schrodinger equation, which of course we've shown earlier in this video. We showed that the Hamiltonian was IH bar d by dt, and when you act on psi, that will deliver you essentially the Hamiltonian acting on psi which of course will deliver you the eigenvalue E on psi. So if I divide both sides of this equation by IH bar, then if I divide this by IH bar, I just get d by dt of psi is equal to 1 over IH bar H psi. But if I multiply top and bottom of here by minus I will get minus I at the top, and minus I times I at the bottom gives me minus I squared, which is just plus 1. So now I've got minus I times H, which is the operator acting on psi. But of course psi can be written in the way that we have written it many times before. Sigma j, alpha j, xj. The superposition of states. Now I want you to compare this equation with this equation here. You'll notice that on the left we have a d psi by dt in both cases. You'll notice that in both cases we have a sum over j term. And you'll notice in both cases that we have a basis vector xj. Now mathematically what that means is that whatever's left, which is strictly called the coefficients, must be equal. But before proceeding with the consequences of that, let's just think about H acting. What's it acting on? It's not acting on the probability amplitude, it acts on an eigenvector. And the eigenvector is xj. What does H do when it acts on xj? It produces the eigenvalue, which is ej. So now we can do what we were leading up to, which is to say that what is left in these two equations must be equal, so that d alpha j by dt, which is this term here, must equal what's left in this equation, which is minus I over h bar ej alpha j. Now whenever you have, and we've seen this before, when you ever have a differential with respect to a term that equals a constant times that term, then the solution is the famous exponential. So alpha j is going to be equal to alpha j at time 0 times e to the minus I over h bar ej t. Alpha j will be alpha j at time t0 times this term here. And this term, of course, we know is a cosine and sine term. It's a sinusoidal term. So effectively, as time goes by, there is going to be an oscillation that is going to arise because of this term here. You can see that at time t equals 0, alpha j will equal alpha j0 times this term. But when t is 0, this whole term becomes 1, because e to the 0 is 1. So alpha j at time t0 is just alpha j0. So if we take our classic term, psi is represented by that superposition of states, better call it over j, alpha j, xj. We've done that many times before. We now have a term for alpha j, when it is varying with time. So psi is equal to sigma j, but now we can put in the term that we just derived, which is alpha j naught times e to the minus I over h bar ej t. And then of course you need the xj term at the end. And that shows you how this value of psi, the state, the eigenvector, the wave function, varies with time. And again, you can see why it's called a wave function now, because e to the minus x, minus ix, is just the cosine of x minus I times sine of x. So this term, and this term of course oscillates, this is just a cosine wave. That's the real part of it, and the sine wave similarly. So this term just oscillates. So you've got an oscillating, essentially, wave function. The wave function oscillates as time progresses.